Welcome to the Explainer. You know, in robotics, you'd think the formula is pretty simple. More brain power equals a smarter robot. But what if that's totally backwards? Today, we're looking at some new research that suggests the real secret to smarter AI might be giving it less to think about.
I know, it sounds a little crazy, right? For years, one of the hottest ways to teach robots has been to build this massive army of specialized brains, where each one masters one tiny little thing. But this new research is asking a really bold question. What if that entire strategy is actually a dead end?
So to really get why this is such a huge deal, we first need to talk about this super powerful and honestly really successful AI method. It's called quality diversity, or just QD for short. The goal of QD is fascinating. It's not trying to find the one single best way for a robot to do something like walk or get through a maze. Nope. Instead, its goal is to create a massive library, like an archive of thousands of different, unique, and effective ways to solve a problem. Think of it like building this giant toolbox of skills. Okay, so a popular way they do this is with something called map elites. The process sounds pretty simple on the surface. It just tries a new behavior, sees where the robot winds up, and if that behavior is either better than what it's done before or does something totally new, it saves it. And then it does this again and again and again, literally millions of times. What you get at the end is what this paper calls an army of policies. And in AI, a policy is basically just a rule book for making decisions. So each policy in this army is like a hyper-specialized little soldier that knows how to do one single thing perfectly, like moving to one exact spot. And this approach has given us some incredible breakthroughs, like robots learning to walk again even after they've been damaged. But this is where the story takes a sharp turn. Because as powerful as this robot army is, this new research shines a spotlight on a critical and kind of hidden flaw in the whole strategy. The problem, in a word, is generalization. See, this army of robots is amazing at solving the exact maze it trained on, but change that maze just a tiny bit, move a wall or shift the finish line, and the entire system just collapses. It's a total failure. Because each little soldier only memorized one specific path, it has absolutely no idea how to adapt. The whole thing is incredibly fragile. So when you really break it down, this method has some serious issues. First, it is ridiculously expensive to train this huge army. Second, as we just saw, these policies just can't generalize. But maybe the biggest problem is that the system never actually learns the structure of the world it's in. It doesn't understand, hey, there's a wall here, or that's an open hallway. All it has is a giant list of memorized moves. So, facing these problems, the researchers set up a challenge. They decided to pit this massive, complex AI army against a challenger that is, well, it's radically, almost laughably simpler. Get this. Instead of an army of thousands, they used just one single robot policy, a generalist. All this little guy knew how to do was move towards a nearby point. And to guide it, they paired it with Dijkstra's algorithm, a classic pathfinding technique from 1959. Yeah, think of it like the original OG version of Google Maps. It just finds the shortest path between two dots on a map. Simple, old school, but as we're about to see, incredibly effective. And the results? They were absolutely stunning. In a standard test called the Ant Maze Challenge, this simple method didn't just compete, it blew the complex ones out of the water. Just look at this table. That top line, that's our simple approach. It explored way more of the maze, over 54%, and it was way more accurate. That's what that low descriptor error number means. It wasn't even a fair fight. But wait, it gets even crazier. Performance is only half the story. The other half is efficiency. To train its army of thousands of specialists, the cutting-edge, state-of-the-art QD method took 15 hours of training time. And this is how long it took the simple, single policy method, guided by a 60-year-old algorithm, to get a better result. About 30 minutes. That is a staggering, mind-blowing difference in efficiency. So what is going on here? How is this even possible? Why did this simple, old-school trick completely dominate a complex modern one? Well, the answer isn't about better algorithms. It's about a better model, and it's one that's borrowed directly from our own brains. The key idea here is something called the cognitive map. It's a theory from neuroscience, and it basically says our brains don't just memorize a list of directions. Instead, we build this flexible, internal map of the world, like a GPS in our head, that understands how different places are connected to each other.
It's this math that lets us find new routes and generalize our knowledge. This is the perfect way to think about it. The Cutie Army's library is like a photo album. It has thousands of gorgeous snapshots of individual places, but absolutely no idea how to get from one photo to the next. The simpler method, on the other hand, works like a real interactive map. It learns the roads, the connections, and the relationships between the points. And because of that, it can figure out a new path to any location, even one it's never seen before. Now, this insight is way more than just a cool explanation for a surprising experiment. It really points toward a fundamentally different way of thinking about how we should be building intelligent machines. So, the path forward isn't about building bigger and bigger armies. It's about building single agents that learn more like we do. Agents that have memory, that build an internal world model, which is basically an intuitive grasp of cause and effect, and that focus on learning the underlying structure of a problem, not just memorizing a bunch of answers. And that leaves us with this really provocative final thought. This research suggests that the next giant leap in AI might not come from more computing power or more complicated code. It just might come from a better understanding and a better imitation of the elegant, incredibly efficient principles that nature already perfected right inside our own skulls.